Okay, I'm ready.
Okay, thanks, Misao. There's a question in chat. If you like, if we could answer that before. So Wang Xingpeng, do you want to ask your question? I can read it if not. It's okay. Okay, I can read. So.
Okay, I'm here.
Sure.
Hello, Professor. I'd like to ask two questions. If we enter a scale factor determining the mass of PBH formed, and the second, if the order 2 solar mass PBHs black holes are detected by LIGO or PBHs, can we confirm the specific time of their formation?
Right. Okay. So this is actually the this figure, huh? So assuming that our universe is almost radiation dominated after some time from inflation to say this recent about the time when the redshift about 10,000. Yes, if you fix a scale, co-moving scale, then it fixes the mass of black hole. And I think I have some simple formula, and which I show you soon. But yes, and at the same time, so if they are LIGO black holes primordial, then we know when they are formed. That's true. I think it was like a PV scale, but I thought yes. I'm not exactly sure. Maybe I'm wrong. But, maybe yeah. Well, I will show you the formula later. Okay. Is that okay?
Thanks a lot. Okay, thanks a lot.
Yep.
Okay, thanks. So I think we can start again, Misao, when you're ready.
Yes. Okay, so let me just discuss a few examples, a couple of examples which can produce some example of a inflationary model which can produce primordial black holes. The one is this is a sort of two-field model. Actually, if you consider a single-field model, it's not so easy to produce peaks in the power spectrum unless you sort of give some fairly ad hoc form of the potential. But if you, as soon as you introduce a second field, then it can accommodate the formation of black hole very easily. So this is one of the examples that you have this so-called R-square inflation model, which produces CMB scale, large scale CMB fluctuations, or large scale structure and so forth. Actually, this is written in so-called the Jordan frame. But if you transform this into Einstein frame, then this curvature, a scalar curvature, essentially plays a role of some scalar field, which is called scalaron. So this was invented by the famous Alexei Stravinsky. Anyway, now you just simply add one additional field, which is in this regional frame, just simple minimally coupled scalar field. I'm adding some coupling to the curvature because if you consider some initial condition for the this universe, then to make this chi field to be almost near the type of zero, you need some potential to make it stable at the type of the origin to be stable. You just so this z parameter is constantly positive. Then adding this term, any small z is okay. Adding this term, this will give you a large sort of a very a positive, the quadratic mass term in the early universe when R is large, the curvature is large. So this is just for technical details. But anyway, the essential point is that you have two fields, and assuming that this early stage, the chi is just sit in the almost chi equals zero. This is chi direction, this is phi direction, so the chi is zero here. let's say it's not really zero, but let's assume that that's zero. Then the phi field or this scalar roll downhill, and then during this rolling you produce the fluctuations which is detected by CMB and so on and so forth. Now at the end of this slow roll, if this vacuum energy is vanishing, then when they oscillate, this would be the end of inflation. But if there is some finite vacuum energy due to this potential of the chi field, then this oscillations actually occurs during the inflation and then turns into second stage where essentially now this Einstein scalar just sit to some given mean value, some constant value, while now the evolution is dominated by chi. So you have kind of this behavior, and the point is that because of this sort of this is kind of this violates the slow roll condition, and you have some fast roll and oscillatory feature. This fast roll and oscillatory feature gives rise to a peak in the power spectrum, which is given like this. So this is sort of a semi-analytic approximation. So if you properly do the numerical computations, probably everything becomes very smooth. But anyway, the point is that if in the original this sort of a stage where the inflation is dominated by rolling in phi direction, the perturbation amplitude slowly decays, as because the epsilon, this is exactly because of this form of the formula. Yes. So here the power spectrum essentially is like h square over epsilon. But epsilon actually depends on k, let's say, at the time of rising crossing. And as k increases, and then you have the decrease in power spectrum. But when it arrives at the fast rolling stage, then as we have just seen in this figure, you have these oscillations and fast roll and oscillation. This oscillation gives rise to a peak in the spectrum, and this oscillation frequency, which is determined by mass of the chi field, determines this width of this oscillation in power spectrum, and this is the parameter which parameterized by the this large M is the mass of this chi field, the second field, and H is the Hubble parameter at the second stage. And if this parameter is large, you have a sharper and sharper peak, as you can see. And this means that you have a very large peak in power spectrum, and sharp peak in power spectrum. And if we recall that this beta is the amount of primary black hole produced, which determines the amount of the current number of relative abundance of primary black hole, is proportional to exponential of the delta critical value squared divided by power spectrum. And if the power spectrum has a very sharp feature, then you will have a very, very sharp feature, or it's almost a spike in the mass spectrum. So this gives rise to a almost monochromatic black hole mass function. And of course, the remaining is just tuning of parameters, but you can just tune the parameters such that this gives rise to the amount of primary black hole, which just explains the total whole cold dark matter. So this is one interesting example, of course. But of course, once you explain, fix some scale and construct a model to explain this region, then you cannot do the same thing for this, let's say, the Rhine-Werder region, unless you introduce another additional scalar field or whatever, and to produce some peak in this direction. In that case, you will have a free scalar field model. But of course, I mean, it's okay to consider such model, but maybe it is a little bit too I mean, ad hoc. Anyway, so but as far as this explaining the cold dark matter is concerned, this is an interesting model which can predict a very interesting predicting amount of black holes, and I will come back later that this is related to the gravitational wave observations. Now, the second one, which is the very recent one, again, those people from China, I considered, is that the so-called resonant amplification model during the inflation. So, in this case, again, you have the two peak, it's the two field. It's similar to the one I discussed in the previous slide. But the difference is that in the first stage, during the first stage, this rolling scalar field it has some, is assumed to have some action like this oscillatory potential, and assuming that this oscillation amplitude becomes larger and larger as you evolve towards this direction, then at certain stage, the amplitude of the perturbation, so this oscillation becomes large enough that you can this rolling field cannot no longer go beyond that point. So then rolling towards this phi direction stops because of this, and they start rolling towards this chi direction. The important thing is that during this rolling through this oscillatory stage, this is if you consider the perturbation follows the effective potential, which is given by second derivative of this, but which also, of course, contains this oscillatory behavior. So this is, again, it's very similar to the Matthew equation, and you will have a parametric resonance of this first model, first, say, fluctuations. And because of this interaction, although the interaction is minimal if there's only gravitational interaction, but you can still produce very large amplification of this fluctuation in chi field. So because of the fluctuation large fluctuation in chi field amplitude can be produced by delta phi, and in this case, in the end, the scalar field phi stops here and do not contribute to the inflation, and which means that they do not produce any appreciable curvature variation by itself, because it doesn't contribute to the dynamics. While this curvature variation can be given in terms of delta chi. So you may have some large, interesting curvature variation, which can produce a kind of black hole at a later time. And for example, this is an example computation that essentially, if you give some particular form of this potential with lambda linearly increasing in phi, then you obtain the curvature perturbation, which is peaked around this the scale which just crossed the horizon when this parametric amplification is largest. So this, for example, this case, then this delta chi is amplified. Other delta chi will not be amplified because delta phi is small, and you have this green line. So this will be this background sort of a level of the fluctuation delta chi, but on this particular scale, there's a resonance which increases delta chi to give a peak. And this, of course, gives rise to a primordial black hole formation at later time. And again, I mean, you can tune the parameter such that it fits to any range. But again, this is to explain some single sort of peak. It is similar to the previous one. The only difference that in this case, this width is not too large, but not too small. It's order of magnitude, it's one order in terms of K. You see this is 10 to the minus 11, 10 to the minus 12. So it's about order one width. And so width is not too narrow, but in some sense narrow enough. It's just very narrow enough. So essentially, again, in this case, almost monochromatic primordial black holes are formed. Now, another interesting point is that it's because of this large amplified fluctuations, although this delta phi does not contribute to the evolution of the universe itself, but because of the fluctuation and well, whenever you have some fluctuation in the energy momentum tensor, you produce gravitational waves. So actually, the gravitational waves are produced during inflation and due to this large amplified fluctuation delta phi. And if you compute this amount of gravitational wave produced from this delta phi, then you find that it's quite large. It can be much larger than this Misao sensitivity. And then in the future, for those models, the scale which let's say produce the primordial black holes to 10 to the minus 12 solar mass, or about 10 to 21 grams or so. So this model can be tested if you actually see whether we see this large gravitational waves, background, cosmological background in LISA. Another thing which actually can, this is one the sort of a greedy scenario which can in principle explain everything, is that so I named it PBH as the MVP, most valuable player of cosmology scenario. Anyway, so this makes use of quantum tunneling during inflation. So it's very different from other sort of scenarios where those peak in the scalar curvature produces black hole. So it's, in some sense, this is a completely different type of origin of primordial black hole. The interesting thing of this model is that what we assume that again you at least need some two field, and let's say, for example, you have some sigma and phi field, and the inflation sort of a slow rolling goes around this circle. So the potential is decreasing in this direction, but potential is higher in this around here. Now, you assume that in this spherical symmetric two-dimensional case, some center of the sigma equal phi equals 0, you have some local minimum. And assume that in the beginning, in the early part of the inflation, the potential energy of the universe is higher than this local minimum in the center. Then there is always is a probability of tunneling this state from this inflating state to this local minimum, and this gives rise to the formation of a bubble of this local minimum potential area, and that's once it formed, then it starts to expand, and expand at the speed of light. But as you know that the universe is also expanding, and it's expanding faster than, in some sense, speed of light. because it's exponential expansion. So eventually, this bubble size is a constraint by some initial co-moving hub radius. But anyway, the point is that so you can form some bubble. Now the point is that if this continues to be the case until the very end, this bubble becomes larger and larger, and the universe becomes highly homogeneous. But inflaton moves along this lowering trajectory, and at some certain moment, the energy density of the universe, the mean universe outside this bubble, becomes smaller than this bubble, which is occupying this local minimum. So this local minimum now becomes a local maximum. And in this case, if you consider the dynamics, you find that actually this bubble will turn into a black hole. And so because of this motion, slow motion, those bubble formed from the tunneling becomes black holes. So in some sense, this is a probing some multi-dimensional sort of some multiverse type scenario. So that's one interesting point. But more interesting is that with assuming the tunneling rate to be almost constant over the say range of interest, then you find that the spectrum in the mass spectrum black hole is given by this empty -1/2 spectrum, and that's the standard case. But of course, our universe could be a matter dominated at certain stage in the early universe, which could be some actually some another primordial black holes, or maybe some cue ball type things or whatever. But we may have some the early universe which are dominated by matter. And if this matter dominant stage is the last in appropriate sort of a time scale, as you can see, this is like maybe in terms of number of equals like 10 or 20. Yes, maybe less than 10. Anyway, then it turns out the spectrum sort of flattens out, and it becomes like this. So this region, this flat region from M1 to M2 is determined by the lengths of the intermediate stage, matter stage. Now, if this happens, then very interesting thing is that this M2 can be of the LIGO black hole scale, and then you can explain some of those black hole mergers. There are some interesting sort of a recent sort of a suggestions that maybe a sort of a this is essentially like this HSC, the hyper spring-come gravitational lensing, micro lensing experiment by Subaru telescope. This is the constraint, but around this constraint, there's one single event which can be interpreted as a gravitational lensing. But of course, if it is a single event, you cannot really prove if it is due to some lensing or not. So, but if you do more and more observations, then you can make sure that it is just some intrinsic stellar sort of a phenomena, or maybe it's really the micro lensing. And so if we do the observation, more observations, that we may be able to actually see such primordial black holes here. So you may be able to explain the LIGO black holes. You may be able to explain this recent Subaru results, telescope result, and you may be able to explain the total contact matter. And even for this large scale, which you have this m to the minus 1/2 tail of gravitational black hole distribution, this can source supermassive black holes. So this is, as I said, it's essentially this. If this happens, this and if in a very lucky case, in some sense, that it can explain all the sort of not maybe all, but most of deep mysteries of the universe. So that's why I say it's a bit greedy. But anyway, it's an interesting scenario. Now, the important thing I haven't touched and maybe mentioned some, but is that if you have this curvature perturbation, going back to this curvature perturbation scenario, then as I said, the large peak of those perturbations will become a black hole, but most of the peak will be, say, as I said, let's say 10⁻⁻1, 10⁻², or so. So when they enter the Hubble horizon, they start to oscillate. They start behaving like a sound wave. And of course, the sound wave can be regarded as because through the Einstein equation, a small but finite oscillations of space-time. So once you have some space-time oscillations, then these oscillations can produce gravitational waves. So this means that once you're given some initial power spectrum of the curvature perturbation, and then you can compute the amount of primal black hole you produce, and also you can compute the amount of gravitational wave you produce. And these are always associated. So it means that if you produce a primal black hole at certain mass scale, there's a corresponding frequency scale where you have produced large gravitational waves. And in this is the sort of conversion sort of a formula or the table. So if the primal black holes, as they call dark matter, and let's assume the mass of primal black hole is 10 to 21 gram, then this will generate gravity. The original the curvature perturbation responsible for this black hole formation will generate the gravitational wave of the frequency of 10 to minus 3 hertz. And this is exactly in the range of LISA band. This is the future space gravitational wave detector plan project. Now, if primary black holes, LIGO black holes, of course, they cannot be the whole black hole, they call dark matter, but still, if you consider the frequency turns out to be about 10 to minus 8 hertz, which is actually the frequency, interesting frequency for the so-called pulsar timing array experiment, by which you can also observe a background gravitational wave of this frequency. Now, this has been already actually discussed almost 15 years ago by these people, Saito and Yokoyama. So if primary black holes, of the say in their case they consider 100 solar mass, but it's within this large sort of scales or digits. This is just a small difference. So you can just immediately consider this. You interpret this in terms of 10 solar mass black hole. But anyway, and total amount of those black holes will be less than, say, in their case, because it's 100 is 10 minus 5. If you make this 10, this becomes 10 minus 4. And considering the h squared, this is about 0.1%. So it's perfectly consistent with this observed merger rate of the current LIGO black holes. And in this case, this amplitude of gravitational wave produced, if the spectrum is highly peaked, it touches those pulsar timing array experiments. And actually, we do have already some very interesting constraints discussed by these people that if PBH LIGO black holes, then even if the amount is small, like 10 minus 3 or so, then it's already on the verge of extinction, meaning that the model can be excluded if you assume a Gaussian distribution function for the density perturbations. Now, as for the this 10 to 20 or 10 to 21 gram black hole, the primordial black hole can be called dark matter, but in this case, it's not still yet in the range of the current observations. But in the near future, when the LISA or maybe Misao and all these other, or maybe these days we have some other plans from China, like Tenchin or something. Anyway, so in this case, the future space interferometer experiment will be able to detect these gravitational waves. Or in the other words, that if they don't observe such gravitational waves, it essentially excludes a model, unfortunately, but excludes a model of cold dark matter as black holes. Okay, now the remaining, I don't know, so this will be until 3:45, is it? So I have maybe 30 minutes, excluding
Yep.
questions. Yeah.
Yeah, that's right.
Yeah. So I didn't have to rush her. Okay. Anyway, so another thing which maybe this is a very, very recent topic which I'm very much interested in is the case where the primordial black holes formed from iso-curvature perturbation. The iso-curvature perturbation is this by that if the name itself tells us that it doesn't originally it doesn't produce any curvature perturbation, any perturbation in the density, energy density of the universe. That's why it's called iso-curvature. So essentially, it's like this. If you have the, this is some spatial direction, and if you draw a graph of the energy density, total energy density, which is given by this red line, is very, very much homogeneous, while some component of the total energy density may be in the form of some other matter, and if the energy equation of state of two different, say it's the matter which contribute this blue line and the remaining part is the same, then this remains iso-curvature forever, and you don't never see any effect of such iso-curvature perturbation until today. But the most probable thing which could happen is that for some maybe non-gravitational formation or some phase transition type thing, let's say, then you may form some inhomogeneity of certain component of the total energy density, and certain component turns into some compact, let's say, compact object. Maybe they could be even black holes, but anyway, and their spatial distribution can be random or inhomogeneous. And in this case, this inhomogeneity can be nonlinear from the beginning, because total energy density cannot be nonlinear, but the local, the separation between, you can separate energy into two different components with an arbitrary sort of a fraction without violating the energy momentum conservation law. So you can have some highly nonlinear large iso-curvature perturbation. And if it doesn't have to be highly nonlinear, but anyway, if you have large enough iso-curvature perturbation in the beginning, and if those fluctuations which form this iso-curvature perturbation behaves like those objects, matter, then their equation state is that the pressure equals 0, while the remaining part is pressure equals 1/2 of the density. So eventually, this sort of a formed sort of a matter, compact object, would start to dominate our universe. So this is the picture, sort of writing in terms of rho A cube, which is the sort of a conserved mass within the moving scale. So if the universe, if you produce some object which behaves like matter, then the matter total mass will be a constant. They will be conserved. While the radiation energy is decreased because of expansion, you have the pressure, and the pressure works against the. If something expands, you lose the energy, as you know. So the energy decreases. So at certain moment, those sort of matter would start to dominate our universe. And if this matter dominant stage is our universe, the current universe today, then this just keep continuing dominating our universe. But if this happens in very, very early universe, of course, then we in order to accommodate the current observation data, meaning that it cannot be matter dominated in a too early universe, then they must decay out. And actually, this does happen to such object like cue balls, that you have some specific time scale where they are those locally formed compact objects decay to radiation. So you go back to radiation. Now, anyway, so independent of whether I come back to radiation, like stays like matter dominated, as I said, initially large ice curvature perturbation, they do not have any effect on the total energy density. But as soon as they start to become dominating, then you will have huge fluctuations in the total energy density. And then this means that the primordial black hole may form if this sort of a clustering is large enough. So this is a sort of an interesting scenario that you may, so actually, as I said, if those small compact object primordial black holes, then actually you form a black hole out of small primordial black holes. Anyway, you can have such interesting sort of a phenomena in the very early universe if once you start to consider some isochromatic patterns. And we do have some. Then, for example, in this case, when assume that this actually happened sometime not too early in the universe, very late in the universe, but and which they call dark matter, and assuming let's say we don't really know what cold dark matters are. As I said, it can be some small primordial black holes. Anyway, the important thing that assuming that they form some very large isochromatic perturbation. And in that case, well, you may constrain the amplitude of this isochromatic perturbation from the observation. And unfortunately, the constraint is very, very weak. But yet, actually, such a constraint has not been discussed until today. So in some sense, although the constraint is very, very weak, as you could see that the amplitude is very large, highly nonlinear. Say here is 10 to minus 4, 10 to 4 and 10 to 10 and so on. But still, this is the first non-trivial model independent, essentially, a constraint on the amplitude of isochromatic perturbation. So, and if the amplitude is very large, you have the very large isochromatic perturbation in the early universe, very, very small scale, then you produce too many black holes. And violate the current observational data. So this is an interesting sort of a new direction. And just very recently, I had those people, actually those two young people I collaborate very often, they were considering the resulting gravitational waves because if you have very large, such a large as a curvature perturbations in the early universe, they will actually probably collapse during the radiation dominance, and which implies that you will produce some non-trivial secondary gravitational waves, let's say. So this can give rise to even stronger constraint than this simple constraint, and probably they will sort of put this on archive hopefully within the month or so. Okay, so maybe I'm rushing too much, so I have plenty of time remaining. We can just spend a lot of time for your questions and answers and so on and so forth. Anyway, to summarize, so the primary black hole can probe the late inflationary stage, and so which cannot be probed by any other means. So it's a very interesting sort of a new sort of areas of study that up to until that, well, if you go back to this, yes, still we so far we only have constraints on this large scale, let's say from 1 megaparsec scale to a 10 gigaparsec scale, so 3 or 4 order of magnitude. But if we start to see, or if you can see some resulting gravitational waves, or maybe the amount of black holes maybe through gravitational lensing, or maybe through other method, then we will be able to see what was happening in the late stage of inflation, and which is a very, very novel feature of this interesting model and scenario. So by the way, and as I have told you that producing primordial black holes generally is associated with the production of gravitational waves. So in this sense, this gravitational wave cosmology, which has become quite important area of research in these days, is closely linked with the primordial black holes. So in that sense, maybe we can say instead of primordial black hole cosmology, PBH-as-VIP cosmology. And that's an interesting sort of areas to study. And for this, up to this point that I was just essentially talking about the curvature perturbation produced in the early stage of the universe, at late stage of the universe. But at the same time, I mean, you may be able to produce some highly nonlinear isocurvature perturbation. Again, most probably the source must be sort of given during the inflationary stage if you want everything to be consistently sort of explained by inflationary model. But in any case, those isocurvature perturbations, which did not play any role until very recently, can give rise to a very interesting sort of phenomenology and plays a very important role in this PBH-as-VIP cosmology. Okay, I think maybe I ended a bit early, but this is approximately the end of my talk lecture, and we have plenty of time for discussions. Okay.
That's great. Thank you very much, Misao.
Oh, by the way, sorry, the final summary I forgot. Anyway, so this is just, I mean, a repetition of the main point of what I have said. Inflation explains observed structural behaviors, as you know, and it explains this horizon and flatness problem, the curvature perturbation. In the standard models, almost scale invariant and almost Gaussian, but they may not be the case. And in the tensor spectrum is also an interesting areas which people really want to detect. in the near future, and if it is larger than say 0.01 or so, then you can discuss lots of interesting sort of phenomenology of the tensor spectrum. And as I said, the late time inflation provides a rich PBH phenomenology, and this is another very interesting topic in the gravitational wave cosmology. Okay, thank you.
Thank you, Misao. Thank you very much. So we have some time for questions. So if you have a question, you can just open your mic, or you can post it into chat. And I can read. Your mic is very low, whoever's asking a question.
Yes, now is it audible?
A little bit better. Can you go a bit higher?
Okay, now?
Yeah.
Yeah, so is it possible that the modes that re-enter the Hubble radius much later and then form the black holes? Or is it only possible in the very early universe during the radiation domination?
Sorry, can you repeat again?
Is it possible that the modes that re-enter much later, maybe
Oh
during
yeah,
matter
that's
domination?
right. So I mean that's another interesting point. This curvature perturbation case. In the curvature perturbation case, the amplitude of curvature perturbation is very strongly constrained, especially in this area, say areas 1 megaparsec or high, a larger scale. But if you consider the isocurvature perturbation actually doesn't play any role in the dynamics of the universe until that component starts to dominate our universe. So, so in this case, actually, I don't know whether you call it primordial, but those primordial black holes will be formed, say, at the redshift of maybe 1,000 or so.
All right.
Yeah. And that can happen if the origin of those perturbations is isocurvature.
Okay. Okay. Thank you.
Okay. Any other questions?
Yes. So, is there an observational way to know that how did these black holes form in the very early universe? Whether by the bubble formation or by some other way? Is it observationally possible to know?
Observationally, probably I don't have any idea to how to actually sort of observe how it is formed. Huh? I mean, what we can observe is only the results of those, say, some gravitational collapse or maybe this large curvature perturbation. So, yeah, you know, we can, for example, this gravitational wave produced from this sort of oscillating curvature perturbation is kind of a side effect. Huh? I mean, if you produce black holes, then as a side effect, you also produce gravitational waves. And so such kind of things, kind of circumferential evidence can be considered, and that's kind of a predictions. And if you, you know, if you can actually observe, say, black holes as well as gravitational waves, then those two observations constraints are, you know, or maybe almost prove your scenario. Yeah.
Okay. Thanks.
Okay, thanks. Any more questions?
I want to ask one more if
Sure.
yeah. So I went through a paper a few weeks ago. I don't remember exactly which one, but is it possible to form these black holes by having a bump in the inflaton field? If there is a very tiny bump or dip, let's say, is it possible to form these black holes, right? And how does that work? I mean, how are these black holes formed by such a bump in the field?
Well, since I'm not the author of those papers, I don't exactly know. But definitely, if you have some bump or something, you break this or violate standard slow conditions.
Okay.
Once you violate standard slow conditions, your amplitude can be enhanced. So maybe that's how they form some large curvature perturbation. It's my guess. Yes, I mean the one necessary condition that's that we use. So you have to break some of the assumptions of the standard single field slow inflation. The simplest assumption is that the single fieldness is violated, so you have some secondary field. Then you can easily make such a peak. But if you stick to single field, you have to violate slow roll conditions.
All right.
Yeah, and so these bumps will do such job, perhaps.
Okay.
Yeah.
Thank you.
Mm-hmm.
So that there's a kind of single field inflationary models where there's a break in the power spectrum, where there's a sudden change in basically the gradient of the.
Yeah, right.
So that they would also produce this PBHs, would they?
That's right. So in those cases also, so you are essentially, well, for example, if you have some potential like this, then it may be slow rolling here, but when you hit this point, then the motion here will not be slow roll. It will be you have some kick, this extra kick from this point, and which means that you are sort of your motion is boosted, and then depending on how it is boosted, that you may have a huge amplification of perturbation.
Okay. So you use so the standards to try and estimate the formation of these things. You use Pressure theory, right?
Yeah.
So, but pressure. I mean, we use that in large scale structure, but it's not very accurate.
I know. So that's really definitely some areas which are not studied detailed yet. But it's the difficulty, of course, is that if you try to do some numerical simulations, the size of black hole is so small.
Yeah.
So it's very difficult to sort of simulate on scales of your interest. And once you focus on single black holes, it's very difficult to say, give some appropriate, realistic initial data. I mean, for example, let's say if you just consider some purely spherical symmetric initial data, right? It collapses. I mean, as long as the size is larger than gene scale, it always collapses the black hole. But in reality, this cannot happen because you have those virialization and the velocity dispersion start coming into play and so on and so forth. But since the Schwarzschild radius is so small, usually it's not so easy.
Yeah. I see.
Mm-hmm. Yeah, but there are many interesting recent work, especially as I mentioned that using peak theory. Peak theory gives you a little bit better description of what is happening. Okay,
because so one of the problems with large scale structure is the objects that are collapsing. So you assume spherical symmetry and a separate universe to model a nonlinear collapse, right? But the collapse, the peaks of a Gaussian random field are elliptical, so you have to do ellipsoidal collapse. So I don't know how that would feed into this.
Yeah. So there are actually there's analysis of the effect of those a deviation from the spherical symmetry. Yes, so many interesting works have been done in these recently, last maybe 5 years or so. So,
But how is
yeah, I mean, there are lots of things to do.
yeah,
But,
sounds like
yeah.
'cause-
And I guess in that sense, yes, those knowledge in the large scale structure can be very, very useful. And if anybody who are interested in the primordial and who has good expertise in the large scale structure formation, that will be very, very helpful. And also, maybe you find it very interesting to work on these things as well. Yeah.
okay. Any other questions?
In the very early times, as we say that the universe was exponentially expanding, right? And now in the very late times, again the universe is exponentially expanding under the dark energy domination. So is it possible that there is an underlying so they're connected, dark energy and inflation in some underlying way? Is it possible?
Oh yes. I mean, not just. I mean, I guess at least there are several models that explains both inflation and the current dark energy. Yes. I mean, it's in some sense highly model dependent or maybe framework dependent. It depends on how you sort of cook up a model and how natural you can do it. Huh? But by the way, so I didn't mention this, but yes. So in all these discussions, I sort of completely ignore the so-called cosmological constant problem, because the real actual sort of vacuum energy, whether it's zero, I mean, it's small but finite, or maybe even negative, we don't know. What we all know is that if there is some kind of a dark energy today, then this scale of dark energy is much exponentially smaller than the scale of this inflation in the early universe. That's all we know, and we don't have any sensible explanation for why that value is.
Okay.
Okay, thanks. So any more questions? You can type them in chat or you can just open your mic.